And for these related rate problems, we'll be given different rates of change and be asked to find other rates of change. And the way that we're going to do that is by making an equation and use the chain rule and implicit differentiation. Woo! That is not even differentiation. There we go. Remember the implicit differentiation where you had x squared plus y squared equals 3x, and you took the derivative with respect to x of the whole thing? And d dx of x squared would just be 2x, but where there's a y squared, you do the derivative as if it was normal, but then you do the chain rule and say, what's the derivative of y? dy dx. And you'd have a chain rule built in with implicit differentiation. We're going to do a lot of that with our related rate problems. So we're going to look at our first example here. We've got a circle. And this circle is increasing in size at a rate of 2 meters per minute. That's pretty fast. If does it say what is the radius? The radius is increasing at 2 meters per minute. So that's getting pretty big, pretty fast. It's already a huge circle because the radius is 100 meters. So this could be a model of something of, I mean, this is probably not changing fast enough to be a model of an explosion, because when an explosion takes place, it goes out in a circle and it increases. And so as it's increasing, more and more area is getting hit by the explosion as time passes on. And if that explosion is traveling at a certain speed, you can figure out how much destruction is happening or at a certain time. And that's what this question is kind of asking us. How fast is the area of the circle increasing at 100 meters? So the way that we're going to set up these problems is first we say, well, what do we want to find? We want to find how fast the area is increasing. So we want to find the change of area with respect to the change of time. That's what we want to find. Now I wrote that a little bit down because if we want to find this, that is telling us that there is some function, area, that is a function of time. Even though we don't know what that function is or what it looks like, there's a formula out there that area is some function of time. As time increases, area increases. We know that the radius is also changing at a rate of 2 meters per minute. So we know that the change in radius over the change in time is 2 meters per minute. And that also tells us that there's a function out there that radius is a function of time. This becomes important because you already know the relationship between area and radius. What is the area formula for a circle? Close. Pi r squared. So there's our formula for area. Area is pi r squared. Notice that the equation that we have here doesn't have time in it whatsoever. It just has area and just has radius. But that does not mean that we can't take the derivative of this with respect to time, and while doing that, use implicit differentiation through the whole thing. So if I were to take the derivative with respect to time of this whole thing, what that would do is it would be the derivative with respect to time of the left side would equal the derivative with respect to time of the right side. And because there's no variable t in this, this is all implicit differentiation. What's the derivative of a if you were doing it just normal? If that was just a variable, what would the derivative be? Close. 1, right? Because the derivative of 1x if you had y equals 1x, the derivative would just be 1. So the derivative of a would be 1, and then you have to say to yourself, I know, and this is why we wrote it at the beginning, that area is a function of time. So then the derivative of area as a chain rule would be dA dt. Similarly, on the right side, pi r squared, if you did the derivative of that normally, would become 2 pi r, circumference. Kind of neat. And then chain rule would say, well, if I did this first, I still need to do the derivative of r, and the derivative of r with respect to time is dr dt. So this is implicit differentiation with a variable that you can't even see in there, but since we know that both area and radiuses are functions of time, we can do that. Now, we wanted to find how the area is changing with respect to time at a certain specific moment. We wanted to find it when the radius was 100, and we know that dr dt is 2 meters per minute. So now we can plug in everything that we know meters per. Since the unit we were using was meters and time was in minutes, this will be meters squared per minute. Which, if you think about that, if we just, pi is 3.14, this is about 1200, a little bit more than 1200. At that moment, when the radius is already 100 meters, in the next minute you could expect about 1200 meters squared more of damage if this was a bomb, or water ripple if this was a water ripple going out. So it tells somebody what kind of damage is happening at that moment, and what is the next, if we don't stop this or stop this from happening to begin with, what can we expect? Or if people need to get out of this area, how much time do they have? So it's a pretty neat application that way.